So our first speaker this afternoon is Luca Mesiti, and he'll speak about Grothendieck 2-topoi, our elementary 2-topoi.
Thank you very much for the introduction and for the opportunity to speak here. This is a really nice conference. And this talk is about a result I've been working on during my PhD, which is that Grothendieck 2-topoi are elementary 2-topoi. And while the theory of Grothendieck 2-topoi is now quite established, they are essentially two categories of stacks. The research on elementary 2-topoi is just at its beginning. And what I wanted to do is showing that Grothendieck 2-topoi are an example of elementary 2-topoi as defined by Weber. And how can I change slide? Like this. And first of all, I'd like to recall the definition of one-dimensional elementary topoi. The most important ingredient is that is the subobject classifier. And the setting is that of a category with finite limits. And the subobject classifier is a monomorphism tau from the terminal object into some omega, which we can interpret as picking true inside the generalized object of true values, and which is universal in the sense that for every other subobject A inside of X, this other subobject can be recovered as a change of base of tau along a unique classifying morphism from X to omega. And the job of this classifying morphism is that of encoding all the information on the subobject in the language of omega, so using the true values that we have. And we can then rephrase this definition in a way which is more easily generalizable, which is asking that for every x, the function g tau x that takes a morphism from x into omega and calculates the pullback of tau along that morphism gives a bijection with the set of subobjects of x. Indeed, surjectivity of this function is telling us that for every subobject, there exists some classifying morphism from x into omega, and injectivity of this function guarantees that this classifying morphism is unique. And you don't need much more to have an elementary topos. You only need to add further finite limits and Cartesian closeness. And somewhat surprisingly, you can immediately deduce a lot of nice properties from just these ones. In particular, every elementary topos has an internal logic, and actually it's precisely the kind of category that you need if you want to do logic inside a category, where finite limits give you conjunctions and Cartesian closeness gives you the implications, for example. And the archetypal elementary topos is the category of sets. The generalized object of true values is here just the set of true and false, and the subobject classifier picks true inside true and false. And it does classify subsets via the classical characteristic functions, which manage to encode the information of subset in terms of a function from X into true and false, sending an element of X to true if that element belongs to A, and to false if it doesn't belong to A. And as it will be important later, I'd like you to notice here how important are the fibers of this inclusion of A inside of X. So we take an element of X and we consider its fiber. And this can either be singleton if the element is in A and this corresponds to true, or the fiber can be empty, and this corresponds to false. And when we go to dimension 2, the fibers will have will be of one dimension higher, so it will be important also to consider the elements of the fibers, rather than just recognizing if they are singletons or empty. And Weber gave a definition of two classifier. The one I present here is actually slightly different. I'll tell you where later more precisely. The setting is that of a two-category with finite two limits, and the two classifier is a morphism tau from the terminal object into omega that we still think of as speaking true inside the generalized object of true values, such that for every x, what is now the functor g tau x that takes comma objects from tau, it gives an equivalence of categories with discrete opfibrations with small fibers. So a few things have changed. Let's analyze them one by one. First of all, we have upgraded the classification process from one regulated by pullbacks to one regulated by comma objects, which is quite natural to do, I think, because comma objects are in some sense a lax analog of pullback in dimension 2. And when you consider comma objects from a morphism which has as domain the terminal object, you just build discrete opfibrations with small fibers. If you don't know what they are, I'll tell you something in the next slide. But keep in mind that they are just what one produces by taking these comma objects. And then we upgrade the bijection that we had in dimension 1 to an equivalence of categories now in dimension 2. If you don't like comma objects, that's fine, because you can equivalently calculate a pullback along a replacement by calculating this comma object along the identity. And this is actually how Weber gave his original definition of two classifier. He kept the classification process to be regulated by pullbacks, but he had to change morphism from the terminal object to general discrete opfibrations from omega bullet to omega. And our definition is actually slightly less general than this, but it's also at the same time a lot useful, much useful in practice to use this slightly less generality. And moreover, it's also closer to the point of view of logic, as now with this definition, we still have picking true inside the generalized object of true values. And another difference with Weber's original definition is that he only asked these functors g tau x to be fully faithful. And the idea is that they will be equivalences of categories with their essential image. So, which can be smaller than all discrete opfibrations with small fibers. So actually, these allow for less discrete opfibrations to be classified by your two classifier. And another justification that we may give to discrete opfibrations is that we have increased by 1 the dimension of the fibers of the morphism that we classify. And the archetypal elementary 2-topos is the two category of categories, locally small categories. And actually, if these weren't true, you should probably change the theory and ensure that this works. The generalized object of true values is now the whole category of sets. So instead of taking just the singleton and the empty sets, you now have the possibility of all possible sets as true values. And true is still the singleton inside of that. And this is indeed the which gives us an equivalence of categories between presheaves and discrete opfibrations. My connection, maybe I didn't choose the best connection. I hope you can hear me.
Luca, you're freezing a little bit, so why don't you...
So we have an equivalence of categories between functors into set and discrete opfibrations on the domain. And this is also called the Grothendieck construction, but keep in mind, be careful that we are considering functors that factorize through sets. So it's the discrete version. And if you don't know what a discrete opfibration is, you can actually read from here that it's a way of reorganizing the data of a functor into set. Without speaking of the entire universe of all sets. And you can view a functor into set as a family of sets. And what you can do is reorganizing all these sets that form the family as the fibers of a single functor into the indexing category. In one direction, the construction of the category of elements calculates this comma object, or equivalently, the pullback along the forgetful from pointed sets to sets, which is the replacement of this one. And in the other direction, if you start from a discrete opfibration with small fibers, then you can consider, you can associate to it a functor into set, sending every object to the fiber on it. And you need small fibers because you need these fibers to belong to set. And after this example, so you can think of a 2 classifier as a kind of category of elements inside your 2 category. So I think it's pretty interesting that subobject classifiers and the category of elements are generalized in the same framework with 2 classifiers. Well, the problem with 2 classifiers is that in practice it's quite hard to check that something is a 2 classifier. And what I've been working on is a reduction of the conditions of 2 classifiers to dense generators. Now, it's not important that you understand the formal definition of dense generator, but the idea is that Yoneda's lemma tells you that in order to get the whole information on an object, you can equivalently look at all morphisms from every other thing into that object. And a dense generator is a collection Y of objects of your 2 category K, such that you can just look at the morphisms that come from the objects of Y. And if this functor J tilde, which is this restriction of the Yoneda embedding to consider only the morphisms that come from Y, is fully faithful, then in some sense it's enough to look at them. And equivalently, if J is fully faithful, we are asking every object F of our 2 category to be a nice weighted 2 colimit of objects of Y, where nice means that they are preserved by this functor J tilde. The archetypal example is that of representables, which are a dense generator for 2 presheaves. And indeed, every 2 presheaves a weighted 2 colimit of representables. And actually here, this functor J tilde is the identity. So nice colimit in this case means just any colimit. And we do have that representables are a dense generator. So now we are ready to look at the theorems I've proved on this reduction of the conditions of a 2 classifier to dense generators. And remember that in order to prove that tau, a certain discrete opfibration, is a 2 classifier, here I'm using actually the version with tau from omega bulletin to omega, you need to prove that all these functors G tau F are equivalencies of categories. This is what means for tau to be a 2 classifier. And the proposition is saying that faithfulness of these functors G tau F can just be checked on the dense generator. So you can just check that G tau Y for Y among the dense generators are all faithful, and then it's guaranteed that all the G tau F will be faithful as well. And the theorem tells you that provided that you already have faithfulness, then also fullness can be checked just on a dense generator. And now we want to keep building on this and speak as well also of essential surjectivity on objects, which is the missing part of an equivalence of categories. And so I proved this theorem that says that provided that you already have fully faithfulness, then also essential surjectivity on objects can be checked just on a dense generator, as long as you can do some operation of normalization. Now, I should mention that this operation of normalization is something that has to do with taking a strict two-categorical context. If you just took a bi-categorical context, then this would be automatic. But I was interested in strict two categories, so I needed this assumption, this extra assumption. I'll tell you something in this slide and then something else later, despite not giving you precisely what this operation of normalization is. And the proof of this theorem is actually constructive. So we have a recipe to build the classifying morphism. We start from phi, a discrete opfibration with small fibers here in the middle of the diagram, and we want to classify it. So we want to build this morphism in blue so that phi is the pullback of tau along this morphism in blue. And what we can do is view F as a nice colimit of dense generators, which we have by definition of density, and try to induce this morphism in blue by the universal property of the colimit F. So we consider all these morphisms lambda that form the cocoon that expresses F as a nice colimit of dense generators, and we consider the change of base of phi along all these morphisms here. So we are reducing the information of phi in terms of this collection of discrete opfibrations over dense generators that we can classify by assumption. We are assuming that we can classify all these discrete opfibrations on dense generators. So we obtain these classifying morphisms at the very bottom, and as long as they form a cocoon, then we can induce the morphism in blue via the universal property of the colimit. And the operation of normalization is precisely what ensures you that you can choose well these classifying morphisms so that they form a cocoon, and then they induce the classifying morphisms that we need. Now, the complete proof is actually pretty hard to achieve, because my idea was to use that pulling back along these discrete opfibrations phi and tau preserves colimits, but these are actually weighted two-dimensional colimits, and so you need to understand colimits in two-dimensional slices, which had not been done before in the literature. And then to do that, I found it useful to reduce weighted colimits to essentially conical ones, which is an existing result, but I think it's not known enough because it's very useful. But I think it's quite good that the statement can actually be easily applied to many situations without knowing the theory that brought to the proof of this theorem. And to understand the benefits of this reduction to dense generators, we can look at the case of cut. Now, you didn't need this theory to understand the two classifier of cut, but I think it manages well to show the advantages of a reduction to dense generator for two classifiers. In cut, we have that the singleton category alone is a dense generator. And so we can just look at a single functor, G tau 1, and what it does is taking a functor from the singleton category into set and produce sends it to the set that it represents, so to the image of the unique element of 1. And this is clearly an equivalence of categories. And so by the theorems of reduction to dense generators, we immediately deduce that the construction of the category of elements is fully faithful, and also that it classifies all discrete opfibrations with small fibers. And we also have a recipe for building the classifying morphism for these discrete opfibrations. We start from phi here, and we view the codomain as a colimit of 1, weighted colimit of 1, and we consider all the change of base of phi along this morphism from 1, which are the fibers of phi precisely. You can characterize the fibers as this pullback of phi along morphism from 1 that pick the element on which you are taking the fiber. And this classify morphisms at the bottom just take the fibers of phi and encode them in a functor from 1 into set, and then inducing the functor in blue just takes the functor that on every object that sends every object to the fiber over it. So we precisely get what we knew of the category of elements, but everything is just deduced from the trivial observation that G tau 1 is an equivalence of categories. Now we want to do the same with the two category of two-dimensional presheaves. So two functors into cut. Here representables form a dense generator. It was the archetypal example I showed you before. And as the representables are a dense generator, we can just look at these functors G tau Yoneda of C. And if you look at the form that these functors have, they are functors from natural transformations between Yoneda of C and omega and discrete opfibrations over the representables on C. And we ask this functor to be an equivalence of categories. So actually, Yoneda's lemma is telling us how we should define the universe omega for two-dimensional presheaf, because this domain is just omega of C, and we want it to be equivalent to discrete opfibrations over the representable. And this is actually a natural generalization of what happens in dimension 1, which is that the subobject on C. But sieves on C can be characterized as subfunctors of the representables. And so remember that we have upgraded the subobjects into discrete opfibrations, so it's pretty natural now to consider discrete opfibrations over the representables, where in dimension 1 we had subfunctors of the representables. And the only problem that we find is that this assignment that takes discrete opfibrations over the representables doesn't give a strict two-functor. This is only pseudo-functorial. And so I was interested in a strict two-categorical context, so I had to do one step further. And thanks to the index Grothendieck construction, which is joint work of myself with Elena Caviglia, who spoke at this pseudo-functor. We can find some omega tilde, which is pseudo-naturally equivalent I think maybe I can change connection.
Luca?
Hi, can you hear me now better?
Yeah, turn your camera off. That might help a lot.
I just changed connection with
right.
the better one, so we can try. If you're not hearing well, just stop me and I'll turn my camera off.
Okay.
You need to share your screen again, please.
Yeah.
There you go.
See it?
Yep, that's good.
Yeah. So I was telling you that the index Grothendieck construction helps us in finding a strictification, an explicit strictification of this pseudo-functor omega by changing discrete opfibrations over the representables in terms with presheaves on the slices. And this is actually totally in line with the paper by Hoffman and Stryker, which wanted to do a similar thing but also different. They kept the ambient to be one-dimensional presheaves, but they increased by 1 the dimension of the fibers of the morphisms to classify. They call them small families. And they managed to prove that this same object is is a classifier for the small families in one-dimensional presheaves. But then they tried to do the same with sheaves, and their candidate didn't work. And the reason is that their candidate is not a sheaf, but only a stack. And what I proved is that the thing that we were considering is actually a two classifier in the two category of stacks. It's the one we will see later. And so this says, in some sense, that if you want to increase by one the dimension of the fibers of the morphism to classify, then you need to increase by one also the dimension of the ambient. And so considering stacks rather than sheaves. And so I proved that taking these presheaves on slices gives a two classifier in two-dimensional presheaves. And actually the proof goes through looking at the bicategorical classifier omega, the one which was a pseudo-functor. So the generalized object of true values is discrete opfibrations over representables, and the true inside of them is the identity of the representables. And G tau Yoneda of C, so for this pseudo-functor, is isomorphic to Yoneda's lemma map. And so it's an equivalence of categories, because it's Yoneda's lemma for a pseudo-functor omega. And from this, we can also deduce that also omega tilde works on dense generators, giving all these equivalences of categories for every representable. And now we want to apply the theorems of reduction to dense generators. And the only thing that we are missing is the normalization process. And to give you an idea of what this is, we start from phi, from G to F, and we want to classify it. So the recipe of the theorems of reduction to dense generators tells us to consider the change of phase of phi along all these morphisms that form the cocoon that presents F as a colimit of representables. And so we reduce the information of phi on in terms of the collection of all these discrete opfibrations over the representables. And we can classify them. We have already proved that we can classify these discrete opfibrations. And the process goes through the index Grothendieck construction. So on every component D, this is telling us to do what the category of elements does. So taking the fibers of this psi on every component D. And the problem is that all these fibers of psi do not really go well together with each other. And what we can do is instead express each of them in terms of fibers of phi, which are global. And this is the trick that ensures you that you have a cocoon, and then that you can induce the classifying morphism from F into omega via the universal property of the colimit. And what I then did was restricting this two classifier to a two classifier in stacks. So just an idea of what a stack is, if you don't already know it. A stack is a bicategorical sheaf. So exactly as with the sheaf, you still want to glue together compatible families of objects. But now these objects are only required to satisfy a descent compatibility up to isomorphisms. So if you take this collection of objects XF associated to the morphism of a covering sieve, instead of asking here for an equality between the descent of the object you chose for F along G and the chosen object for the composite of F composed with G, you just have an isomorphism here. And you want this isomorphism to be coherent as it is expressed by the square below, which is called cocycle condition. And this says that the isomorphism that regulates the descent along G, followed by the isomorphism that regulates the descent along H, is the same of the one that regulates the descent along the composition of G and H, up to add this isomorphism that is given by the fact that F is only pseudo-functorial. And so we want to restrict the two classifiers that we have in two-dimensional presheaves to one in stacks that are strictly functorial, because we want them inside strict two categorical presheaves. And what I mean with restrict these two classifiers is that we search for some omega j, which is a stack, and of an embedding of omega j, or rather its underlying two presheaf inside omega tilde. And this means that instead of considering all these presheaves on slices, we just chose a bunch of them. We select these presheaves on the slices, and we want to take not too many of them in order to have a stack, but at the same time enough of these presheaves to guarantee that the classification process still happens also in stacks. Which means that if we start from phi with H as stack, a discrete opfibration with small fibers, with H as stack, and we assume the topology to be subcanonical so that the representable is always a stack as well, we can classify this phi in two-dimensional presheaves. So we find the pullback square behind in this diagram. And we want the classifying morphism key here to factorize through omega j. So in this sense, we need to take enough presheaves on the slices so that we have this factorization here and ensure the classification still happens with omega j instead of omega tilde. And if this is true, then you can consider the pullback on the right portion of the diagram to find the two classifiers in stacks. Here on the right, we have the two classifiers in two-dimensional presheaves, and we consider the pullback of it along this embedding. And as we have a pullback behind and the pullback in the right portion, by pullback's lemma, you find that also the left portion of the diagram needs to be a pullback, which means precisely that you find the classification also in stacks. And the solution is to restrict presheaves on the slices that are sheaves with the topology that you were considering for the stacks. So taking sheaves is something that it's a choice which is tight enough to get a stack, which is also a strict two-functor, but at the same time loose enough to have this factorization here in the bottom part, and so ensure that everything works, at least on dense generators. So we now know that at least on dense generators, everything works for a two classifier in stacks. And we apply the theorems of reduction, so we are only missing the normalization process. And the normalization process can be done in functorial stacks. The normalization process can be done in two-dimensional presheaves, meaning that if you start here from some key that are chosen well, that are chosen normalized, then the key phi j that you induce by this factorization will be normalized as well. And so by the theorems of reduction to dense generators, we conclude that taking sheaves on slices gives two classifiers in stacks that are strictly functorial, and this classifies all discrete opfibrations with small fibers. And I leave you with some references. Thank you very much for your attention.
Okay, let's thank Luca for a great talk.